Okay, so I'm going to discuss the solution to this problem, but at the same time, I will also use this problem as a context to talk about other things. So assume that the pitching moment curve for the landing configuration for the airplane analyzed in example problem 2.2 at its forwardmost center of gravity position is as follows. So the equation for the moment coefficient about the center of gravity is given, where alpha is in degrees. Estimate the size of the elevator to trim the airplane at the landing angle of attack of 10 degrees. Assume that the elevator angle is constrained to plus 20 degree and minus 25 degree. So this is the limit to which you can deflect the elevator. So the question is basically saying that we want to land this aircraft at an angle of attack of 10 degrees, and the maximum you can deflect the elevator is plus 20 degree to minus 25 degree. So what should be the size of the elevator? So what should be the area of this elevator, which will allow us to perform this operation? Now there are a few things here that can be pointed out, taking advantage of this context. Okay, the first thing is, see, in the previous example, which should still be there. Okay, in this example, when we had to trim the aircraft at a higher value of lift coefficient, the solution was to shift this CM versus CL curve in towards the right. Okay, so graphically speaking or mathematically speaking, we just shifted this blue line to the orange line so that we could trim the aircraft at a new value of CL. Now forget the physical components. If you just think of this mathematically, so let's think of these things mathematically, and then we can try to imagine how such mathematical conditions can be fulfilled physically. Okay, so we can try to build a solution with this sort of thinking also. So how about if I want to trim the aircraft at a higher value of CL? In other words, if I want to fly the aircraft at the same altitude at lower cruise speed, instead of shifting the curve, maybe I could have changed the curve and made it like this, right? I could have changed the slope of the curve instead of shifting the curve. And now I can start thinking like, what can I do to the aircraft so that the slope would change instead of shifting? So one of the ways in which you can change the slope of the CM versus CL or CM versus alpha is by shifting the center of gravity location. And that you can also see from the equation for CM alpha. Yeah, take the equation for CM alpha due to wing, right? The contribution to CM alpha, which is the slope, because of the wing is equal to CL alpha W x CG over C minus XAC over C. Now here I'm only including the wing contribution, and you could include other things as well. But just as an example of one of the ways in which the slope can be changed, you can see from this equation that if I change the center of gravity location, the slope will change. This will change, right? And if this will change, then the overall CM alpha will change. So we could have trimmed the aircraft at a new value of CL by changing the slope as well. So how do we do that? Now in this particular example, how has the slope changed? The slope has become less negative. So if I move the center of gravity more towards the tail, the slope will become less negative. So we will shift from this blue line to the green line. Okay, so you can imagine that I add more weight towards the tail of the aircraft somehow. Maybe I will move all the passengers towards the tail, which will somewhat help me to shift the center of gravity towards the tail. And then I will get this, and I will be able to trim the aircraft at this higher value of the lift coefficient. Now coming back to our example, we are dealing with the landing configuration. We are dealing with the landing configuration. Now during landing, the landing gear is deployed. Okay, the landing gear is deployed, and the flaps are also deployed. The flaps are extended. So this ends up moving the center of gravity towards the nose of the aircraft. So it will make the slope of CM versus alpha more negative. The note is that the CM alpha is more negative during landing as XCG moves forward. Because of the deployment of landing gear and flaps, right? All the extensions from the wing and the flaps. Okay, so what else can we imagine now based on just the situation that we are in here? So when the center of gravity moves forward and the aerodynamic center stays at the same place, this will end up increasing the moment. Okay, so imagine this line. Previously the center of gravity was here, and now the center of gravity is here, just an acceleration. And let's say the aerodynamic center is at the same location. So when the center of gravity moves forward, you can see that the moment increases because the distance between center of gravity, which is the turning point, and the location where the force is acting has increased now. So this will lead to an increase in moment. So during landing, because of this change in the center of gravity location, the aircraft will want to pitch downward. Okay, because now this extra, the aircraft needs to be balanced, okay, by overcoming this extra delta Cm which is created. And this extra delta Cm is trying to pitch the aircraft downward, which means it is negative. So we want to create a positive delta Cm so that the aircraft can be stabilized at this high angle of attack with the landing gear and the flaps deployed. So to create this positive delta Cm, now we can imagine how we would deflect the elevator at the tail, right? So if the elevator deflects upward, then this will try to pitch the aircraft nose up, right? Because an upward deflection of the elevator will create a downward lift force, and this will create a moment in this direction, right? In the direction which is opposite to where the aircraft wants to turn. So just based on the scenario that we are given, we know that at some point in the solution process, the value of delta that we will have to use has to be negative. Okay, so in case we have to use the maximum value of elevator deflection, then we will be going with negative 25 degrees and not plus 20 degree, because we know that during landing the elevator has to be deflected upward based on our physical understanding of the problem. So in case there comes a point where we have to choose an angle for the elevator and we have to choose the maximum value, then obviously it's going to be negative 25 and it will not be plus 20. This is based on our understanding of what is required to make the aircraft stable during a landing approach. So the equation is given: CmCg equals to minus 0.20 minus 0.035 alpha. So estimate the size of the elevator to trim the airplane at the landing angle of attack of 10 degrees. So the first thing we need to know here is the moment which will be generated on the aircraft when it pitches at 10 degrees. Okay, so imagine that the aircraft was flying in some steady state. Now it wants to maintain an angle of attack of 10 degrees. Then what will be the moment about its center of gravity? So that is possible to be found by using this equation: CmCg equals to minus 0.20 minus 0.035 times 10. So we know that if we do not use the elevator, if we just let the aircraft pitch at 10 degrees, then a moment will be generated which will be equal to negative 0.55. So as we had predicted, there is a negative delta Cm which is produced during the landing process. Now it has to be overcome with a positive delta Cm generated using the elevator. So the moment which is generated by the elevator deflection will be Cm delta E times delta E. Right? This is this extra delta Cm elevator. Okay, so just to make you more comfortable with this, think about the equation for Cm. The equation for Cm was Cm0 plus Cm alpha alpha plus Cm delta E, and this is the part that comes from the elevator. So here we are talking about generating some positive moment using the elevator. Okay, and this has to be equal to plus 0.55 because the aircraft is experiencing negative 0.55, just like in the example I had discussed. Now we want to cancel that negative with positive, so we want to generate positive delta Cm. So that's why Cm delta E times delta E is equal to plus 0.55. And then we can solve for Cm delta E. This will be equal to 0.55 divided by delta E to solve for size of the elevator. So let's try to see where that arises. Minus VH eta. Now this delta CLT is that delta CLT can be written as dCLT d delta E times delta E, and we have the equation for this here. So this is equal to minus VH eta CL alpha T times tau times delta E, right? So I have substituted CL alpha T times tau for this dCLT delta E. So this is the gradient, right? So this is the Cm delta E. Now, of course, all this is already in our notes from a previous lecture, but I just want to connect it to the summary that we were writing today as well. Okay, so what this tells me is that Cm delta E equals to minus VH eta CL alpha T times tau. Tau is the flap effectiveness parameter, and this is what I need. So here Cm delta E is equal to minus VH eta CL alpha T times tau, and this is equal to 0.55 divided by delta E. So still, where is this area or size of the elevator? Well, that is contained in the tau. I can say that tau equals to 0.55 divided by delta E over minus VH eta CL alpha T. We know that the elevator has to be deflected upward based on our understanding of what is required to stabilize the aircraft during a landing approach. So if we have to choose one of the limiting values, then we will choose negative 25 degrees. So in this delta E here, we have to choose negative 25. We have to choose negative 25, and you need to understand that this would lead to the lowest value of tau, right? So in other words, the answer we will be getting will be the minimum value of the size of the elevator. Okay, just a note here that when delta E equals to negative 25, and we should choose negative, we will get minimum value of tau which will give minimum value of SE, right? Because tau is directly proportional to SE over ST. Okay, that's good. So we know that we will put a negative 25 here. Now the tail volume ratio VH, what will be the value of VH that we will put? The tail volume ratio is equals to ST times LT divided by SC bar. And ST is given to us here. I think this H here is the horizontal fin, which is the tail, and LT is given to us. The area of the wing is given to us, and the wing mean aerodynamic chord is also given to us. So you can calculate the value of VH. Now this tail efficiency factor, unless it is specified, you can assume that it is equal to 1, because that is what seems to be done in most cases. And as we know, most often this value of eta varies between 0.8 and 1.2, and it is greater than 1 if the tail is in front of the wing, and it is less than 1 if the tail is behind the wing. So when you say eta equals to 1, it, I think, is a good approximation, okay, unless it is specified. Now we need this CL alpha t, but we don't have this CL alpha t. We can calculate the CL alpha t from CL alpha for the tail. Now there is a difference, as we have discussed in the past, between this CL alpha and CL alpha. See, the CL alpha is for the airfoil. Now we are concerned with the tail and not just the airfoil, right? So you can calculate it using the appropriate equation. To find this CL alpha t, you can write CL alpha t equals to CL alpha tail divided by 1 plus CL alpha tail divided by pi AR. The problem is you don't have the aspect ratio of the tail. You have the area, but you don't have the span length of the tail, do you? You don't. Okay, so there seems to be some missing information, which is all right. Just to discuss the example, this will not happen during a test, okay, but the idea is that you will obtain the value of this CL alpha t and you'll put it here, and that CL alpha t may have to be obtained based on the airfoil information if it is not directly given to you, and in case you have to use the information given for the airfoil, then you will use this equation. Okay, so in this way you will find the value of tau. Then what you will do is you will go back to the plot of tau versus the area ratio. It will be provided to you, and let's say you found the value of tau, which is something, let's say 0.5. Then you will read from the plot the value of this area ratio. So in this way you will obtain SE divided by ST, and it will be some number, let's say it is 10. Then the area of the elevator would be equal to 10 times ST. So you need to know the area of the tail. So area of tail can be obtained again from the information which is provided to you. It is important that you understand this example very clearly, because you will have to use this type of thinking in your project as well, because there you have to find the size of the rudder. Here you are finding the size of the elevator. Here you are trying to balance the extra moment which is created because of the shift in center of gravity in the forward direction. In the project, you are trying to balance the extra moment which is created because of the single engine operation, because there one of the engines shuts down, so there is only one engine working. Some moment will be generated, so you have to overcome that extra moment. using the rudder. Here you are overcoming this extra moment because of the landing gear deployment by using the elevator.